Okay, I think we can start. So welcome back, everyone, after the summer break. These are the young seminars. We have today, as usual, two speakers, Federico Balducci and Alessandro Santini. We will start with Federico. Let me just say a few words to introduce him. Federico, he got his bachelor and master degree in physics in Rome at Sapienza University. Then he completed his PhD in the statistical physics group at SISA in Trieste under the supervision of Professor Antonello Scardicchio from ECTP. He is currently a postdoctoral researcher at the University of Luxembourg, having Professor Aurelia Chenou and Professor Adolfo Del Campo as supervisors. His research interests lie at the intersection of quantum physics and statistical mechanics, topics as the dynamics of quantum many-body system and disordered systems as glasses or spin glasses. The title of his seminar today is Subdiffusive Spin Transport in Disordered Classical Heisenberg Chains. Federico, you can start sharing and start your presentation.
Do you both hear me and see my screen?
Yes, it's okay.
Okay. Can I start? Hello?
Yeah, you can start.
Okay, thank you. So in this work, so thank you for having me here at this nice series of seminars. This work that we'll be presenting was done in collaboration with Antonello Scardicchio. As was just said, he was my PhD supervisor, and other two people in Dresden, Frederic Mössner and Adam McRoberts. Now, actually, Adam is going to go to ICTP, so he's coming to Italy. And just as a disclaimer, Dresden and Trieste are no more places in which I work now. I work in Luxembourg, which is this small place here in these two groups that were cited before. So let me go into the matter. What I'm going to be speaking about is the problem of transport in a disordered classical Heisenberg chain. So I will start by introducing what is the problem with this classical Heisenberg chain. And I will try to motivate why the problem that we study is interesting from two perspectives. One is the model itself, what was already done. And the other is because is actually the route we came to this model. So from the problem of quantum localization and what happens correspondingly in the classical version of the same models. And this talk will be mainly due to review of these two topics. And then very briefly at the end, I will show you what we did new. Actually, what we did was to show that in this disordered classical Heisenberg chain, there is a series of transition from diffusion to slow diffusion and finally to subdiffusion. So let me start from the classical Heisenberg chain per se. We know that nonlinear models can give us many surprises. For example, these are the famous plots taken from the Fermi-Pasta-Ulam-Simbu paper. So we see here that even on very long time scales, there are revivals to the initial state. And so the people did not expect that nonlinear equations could host long-lived memory of the initial state. But this is what happens. And the same happened also in the classical Heisenberg model, which is another non-integrable classical model. This is the Hamiltonian that I would have in mind. So it's an isotropic magnet on a line. And these are the equations of motion. You see they are nonlinear. The spin enters quadratically on the right-hand side. And people would have expected usually that this model would just give diffusion of spin and energy. But in 1988, a first numerical study showed that apparently, this is the line that you have to look at, apparently the transport was super diffusive in the model. Soon after, other people claimed that instead, if one goes to long times and to large system sizes, diffusion is restored. But this was not the end of the story, because alternatingly in the years, people have claimed one or the other thing. So the phenomenon, the nature of transport in the classical Heisenberg chain have been discussed for a long time. Then the issue went again under the spotlight, because in the quantum counterpart of the model, so the XZ model, at as an anisotropy parameter equals 1, it was found in this rather famous paper now that there is a superdiffusion of the Cardar-Parisi-Zhang type universality class. And so you can see from this plot here that there is not a light cone which is linear, so it's not ballistic as you would expect from the hydrodynamics theory, but instead you have a t to the 1/3 typical scaling of Cardar-Parisi-Zhang. So there were several works trying to understand why in this quantum counterpart one does not have either diffusion or ballistic transport, but something between. And the more people, and actually people have also started to study again the classical model in order to shed some light on the quantum case. And this is the what Adam and Roderick and other collaborators did in this paper here, in which they show that actually there is a lot of things going on. It depends, for example, if you take your J to be positive or negative. So if you have a ferromagnet or an antiferromagnetic model, it matters in the dynamics. And what they saw is that also depending on the initial energy of the state that you evolve, also if you sample your initial state from a high temperature distribution or low temperature distribution, there is a difference. And what they found is that in the classical model, there is indeed a possible KPZ scaling. You see here a diffusive exponent of almost 2/3. So in what people have put forward for this kind of explanation is a connection to an integrable classical chain that itself shows a complicated panorama for the transport properties. So I will not go into that with much detail. I just want to point out these nice works here that highlight how the presence of solitons really affects the dynamics. So solitons are well defined for this integrable chain. They do not exist in the Heisenberg chain from which we started, but the proximity in some sense of these two models makes the presence of metastable solitons responsible for anomalous transport in the XXX chain. So this is one possible way of motivating why one wants to study the transport in the classical Heisenberg model. And this is how Adam and Roderick went to the problem. But from the side of me and Antonello, we come from a different community, the community of localization and also subdiffusion to some extent. So let's say we work on topics that are surprising as well, but happen in the linear domain actually. So if one has to go back, to Bloch himself when he wrote down the tight binding Hamiltonian, and he found out that it does not transport. If one puts quantum particles that hop on a lattice and turns on an electric field, one does not get actually transport. Instead, the eigenstates of this model are localized, and one can think of it as the effect of backscattering of photons, of particles on the lattice because of the finiteness of the kinetic energy band. And so people thought, okay, but this model is too idealized. There will be for sure some little impurities in the lattice, and these impurities will make particles scatter, so transport will be restored. And then another surprise came in this now milestone paper by Anderson, in which he showed that in 1D, any amount of disorder will actually localize again the eigenstates, so that transport is not present. The same in 2D, and in 3D, one needs to put disorder strong enough in order to have a localization, but still there will be a localized phase. So again, if one wants to see diffusive transport and electrical conductivity, one has to pay attention to what model it takes, because it may be too simplified and things can go not as expected. So the next thing to do in this kind of models is to add interactions. And in particular, you see that it is known now, you can go to textbooks of condensed matter physics, that if you put both an electric field and interactions, finally you have diffusive transport. And with diagrammatic perturbation theory, you can compute your diffusion constant and thermal conductivity and so on. However, people from the community of the Anderson localization wondered whether the same happens when you start from your initially Anderson localized model and you put interactions on top. And first there were some papers that were arguing that there should be a localized phase, but the final evidence came from this now famous paper by Basco, Lehner, and Schuler, who really did very difficult work at all orders in perturbation theory to show that if you put interactions back in the game, but the lambda is too small here, then the localized phase will remain stable. So you have a model which should be chaotic when you just write it down, but it is not if you really consider all the details. So since 2005, 2006, a lot of interest has grown for these kind of models. And what does this model has to do with the Heisenberg chain? Well, if you are in 1D in particular, you can use a Jordan-Bingen transformation and basically map this model here to the XXZ chain. Then you can turn lambda to be 1 so that you get a Heisenberg chain plus a fluctuating disorder in the Z direction. So a lot of a huge amount of effort has been devoted to these kind of models. And what mainly people were able to do was numerical studies, which, however, are confined to very small systems. And people have also worked out some analytical explanations on why there should or there shouldn't be localization in this model. The issue is not completely settled yet. And in particular, the point is that small system sizes and complementary to that, small times for the dynamics force one to not to explore the physics of non-perturbative effects. That, on the other hand, from theoretical arguments, have been argued to be very important in this model. So the problem is that one would like to explore the physics of very subtle effects that become relevant at large system sizes and large times, but we cannot because of the difficulty of simulating quantum systems. So just to give a flavor of what has been done so far, one can basically use two directions. One can go to the spectrum of the system, so one can perform exact diagonalization of the Hamiltonian I showed before, and one can show that there is a transition, at least, so this is finite side, so a crossover maybe from a regime of Eigenstein thermalization hypothesis, so chaos, and from the spectrum one can see it via the use of the Boygas-Giannoni-Schmidt conjecture for the energy level spacings. And on the other hand, if you ramp up the strength of your disorder, on-site disorder, you should end up in a phase which is so-called many-body localized, and where the spectrum obeys the Berry-Tabor conjecture. So this is one possible way of approaching these quantum models. The other way is really doing the time evolution of a system. If you are interested, I suggest you to look at this paper. It's one of the most recent and precise numerical explorations of the dynamics of these kind of systems. But also here, the problem is that you can either have very small system sizes and go to long times, or another plots that do not show, you go to very large system sizes, but to very short times. And you are not able, just from numerics, to look at these curves and conclude, yes, this curve will stay below 0 so that the correlation does not get to 0 at infinite time, or no, look, this curve will slow down, but eventually go to 0. So it's very, very difficult to understand from these kind of simulations what are the effects of taking the system larger and larger and times longer and longer. So why don't people just use semi-classics? So why just don't people go back to the classical model to explore this kind of physics? Well, it was long known that simple semi-classical analysis does not work to explain localization, already at the level of the Anderson localization without interactions. So basically, if one computes the diffusion coefficient in the semi-classical picture, they will find a diffusion coefficient which is always non-zero. But we know from the full solution of the model that diffusion coefficient drops to 0 in a real transition. You see here you have a non-analyticity in the diffusion coefficients. You have a phase transition, a point where the sort of high temperature expansion fails to be precise. And why does not the semi-classic work? Well, because Anderson localization takes place because of the phase coherence between successive scattering events of the particle on all the impurities. And the semi-classical treatment basically assumes that the particle propagates freely between these scattering events, losing during time, the phase coherence that instead leads to localization. But this didn't stop people from going back to the classical model and studying blindly what happens for the dynamics. So in this paper by Oganesian, Hughes, and Pal, it's actually a very nice paper. And it was published very soon after the discovery of this putative many-body localized phase. What they did was to just study with numerics blindly the dynamics of the classical counterpart of the model that has been studied so much in the quantum realm. And what they found is that even if the diffusion constant is always non-zero, it drops down a lot when you reduce the strength of the Oppingen interactions. And so you see here that you get 10 to the minus 6 diffusion constant here. So even if you go to larger system sizes, because the system is classical, you need to go to very large times in order to really understand that your system is diffusive and it's not just stuck in one position and thus localized. Another interesting thing that they found in this paper is that not only diffusion constant is very small, it also has anomalous contributions at finite time. So it's really difficult to just use numerics to pin down these effects. You really have to push your computer to the best it can do. So this wanted to be a sort of recap of what was known already on this model, and let me now go to what we did new on the topic. So for some reasons, for the reasons that I talked about, plus other that I do not have time to introduce, we were led to consider this version of the model which has disorder on its bonds. And the idea was that if we put an extremely strong disorder here on the bonds, where in particular we will make some JIs be very, very small, we can have bottleneck effects for the transport. So you can look at here for the probability distribution that we chose for the bonds. You see that if eta is less than 0, there is a lot of weight on j equals 1 and a little weight for 0 bonds. Eta equals 0 is the marginal case in which you start to have a finite weight for 0 bonds, and eta larger than 0, it's still integrable, it's still a probability distribution, but a lot of bonds will be almost 0. And so you will have, in a large chain, a lot of effective cuts that slow down a lot the dynamics. And these effects of cutting the dynamic can be seen from the inverse coupling, because it's 1 over the energy that defines the time scales. So basically, from now on, I will reason in terms of these 1 over j's, which become very, very large in the case eta greater than 0. So this means that the time that has to pass in order to see diffusion has to be very, very long. So these are the nonlinear equations of motion that we integrated numerically with a symplectic integrator. Otherwise, you lose all the structure of your problem. And what we considered was the correlation function. We basically assume that the correlation function, when it is averaged both over the initial state, over time, and over the ensemble of disorder for decouplings, as a scaling form, which with possibly an exponent which is not simply related to diffusion. So if this alpha is 1/2, you have diffusion. And so what we did was to consider actually the autocorrelation function, so that we rid of this f function, we just have this prefactor in front. And if we now fit the autocorrelation function, we can extract this alpha. And our result is to claim that as long as eta is less than 0, there will be diffusion, but with very strong finite time corrections. And then eventually subdiffusion will kick in. So how do we understand why there should be diffusion or slow diffusion or subdiffusion? In the end, it all boils down to the existence of the moments of the inverse couplings. So if 1 over j exists and 1 over j square average exists, then basically you can apply central limit theorem analysis and diffusion will hold. This model will not be much different from the model that has j everywhere constant on the chain. But instead, if the first moment still exists, but the second moment does not exist, what happens is that at infinite time, well, there will be still diffusion, because one can basically take an average of the equations of motion and go back to the diffusive case, but the finite time corrections will be governed by an anomalous power, because the second moment here, so the fluctuations are divergent with the sample sides. And this has strong signatures on what you find from the numerics. And finally, if also your first moment of the natural time scale of the problem diverges, you will go to a subdiffusive phase. So if you have to look at the data, this is what you would see. So these plots are plots of basically the same data. We are scale collapsing the correlation function. And here on the left, you find the scale collapse with our best guess for what should be the form of the asymptotic plus finite time correction. So you see here that we were able, with this ansatz here that I will motivate in a few slides, to capture pretty well both the scaling of the autocorrelation and of the tails of the correlation. If instead you tried to only scale with the asymptotic behavior, which is diffusive, you get a terrible collapse. And even if you tried to scale collapse the same data with an effective subdiffusive exponent, you would get a scale collapse which is kind of okay, but then when you go down to the details of the problem and try to understand it analytically, you will face some contradictions, which, however, I do not have much time to discuss. So this is the case in which the first moment of the inverse coupling exists, and we claim that it is a diffusive regime, but with very strong anomalous finite time corrections. Then if you actually go to the case eta equal to 0, which corresponds to a finite weight to the j equals 0 couplings, you will get still diffusion asymptotically, but now the first correction is logarithmic and it goes together. You cannot say that at infinite time it's really diffusive. You have a logarithmic correction. And again, using these ansatz, you can fit much better the data with respect to a simple subdiffusive picture. And finally, if you go to the case in which the disorder is ultra strong, of course, you get subdiffusion with both first, how do you say, a leading behavior and subleading behavior, which are anomalous at infinite time. And here you see very well that the scaling collapse for our model with the subleading corrections performs much better than the simple scaling collapse for the subdiffusive behavior, which is asymptotically taking in. So how did we get those strange forms for the function that we use to fit the data? Well, we basically linearized the dynamics in the following way. We assumed that we could coarse grain the local conserved quantity, and that this local conserved quantity would undergo a motion which is linear and governed by an effective diffusion constant, an effective local diffusion constant, which shares the same fat tails of the distribution of J. There are some reasons for which this model is the correct way to linearize the dynamics. It's sort of empirical, but it works very well. And also we chose to remain on the lattice instead of passing to a continuous hydrodynamics just for convenience of computation. So we realized that this model here was studied a long time ago, and it was solved with a lot of different ways by all these people. And this was known as the random barrier model. And the dynamical phase diagram of this model was the object of several important papers back in the 80s. And this model basically is describing the diffusion of a conserved quantity into a medium which is disordered. And it was shown that only in one dimension there would be subdiffusion. So if you would study the same model in more dimensions, you will always find diffusion with less severe corrections, which hints again at the presence of bottlenecks due to the topology of the 1D lattice. But we didn't know that this model could be solved in all this way when we wrote it down. And so we solved it via another method, which works as well fine, and also has the advantage that can allow one to access the finite time corrections to the asymptotic scaling. So we basically put the equations of motion in Fourier space in a sort of transfer matrix form. And we then expanded in powers of omega the equation that you get by iterating this matrix multiplication. And then we grouped together all the terms. And to be fast, because my time is running up, what you can do from this sort of expansion, you can understand when taking the average now of this sort of magnetization, coarse grain magnetization, you will see that you have the averages of the inverse of this D, which is distributed as the same as J before. And so you can relate the time behavior at infinite time, a little bit less than infinite time, and even shorter times to the divergence of the moments of the distribution of D. And this is the, I don't want to be very, to go much into the details. This is the kind of expressions that we find. So basically, we are able with this kind of transfer matrix method to isolate both the asymptotic, in this case, diffusive, because the time scales as the times over space scales with a factor of 2, and the anomalous corrections. So this method allowed us to, for a simpler model, to really write down sensible ansatz for the way that the conserved parameter is moving in the chain, and allowed us to arrive to those strange forms we were having for the fits. And using that form, we were able to have a scaling collapse that went well both for the tails and for the autocorrelation function, which was not what we were being able to have before going to this simplified model. What we were trying to do was to just fit with a simple asymptotic subdiffusive behavior, but then we were getting poor quality fits and also simple analytical arguments that were not really matching what was happening. Here instead, we have a toy model which is linear, which is fully under control, and they can explain both the infinite time and finite time behavior for this kind of systems. So I was quite fast, I realized, but the time is finishing. So let me jump to the end of our slow subdiffusive journey and the conclusions. So I hope I convinced you that there is a very interesting dynamical phase diagram in the Heisenberg chain, both with and without disorder. And for the case we consider, for the case of disorder, we consider we could point the finger towards bottleneck effects that are the ones responsible for a very slow diffusion or subdiffusion. And the point we want to stress is that strong finite time corrections really make it difficult for people to extract the analytical behavior of a system just from the simple data. In fact, people have discussed for 30 years on what was the origin or what was the nature of the either diffusion, superdiffusion, or subdiffusion in the Heisenberg chain, but only when the hydrodynamics was developed in the clean case, things were really settled. The same will happen in the quantum case, sorry, in the disordered case, both for classical systems and quantum. So if you want to fit something which is very slow and needs large system sizes, you better have an analytical theory behind to guide your intuition. So I think I'm eaten up my time, and I finish here. Thank you.
Okay, so thank you, Federico, for this nice seminar. The session is now open for questions. Are there any questions? I don't see any. Maybe I have one curiosity. And my first question is, from which state do you start your dynamics?
So we basically extended to the disordered case what was done in this paper here for the classical case. So we have data both starting at infinite temperature and then lowering the temperature in order to probe different zones of the phase space. But then the data that I've shown was all at infinite temperature. So basically we choose an infinite temperature state and evolve it. This was motivated by the parallelism with the quantum case, in which usually one wants to see whether there is localization for all states. So the middle of the spectrum is the one that is more unlikely to localize because you have more energy to go around.
So you start at infinite temperature and then you evolve at a smaller temperature, or still at
no. We sample the initial state from an infinite temperature distribution, and then we evolve by perfect energy conservation equation of motion.
Okay.
So we are talking about closed systems. The only thing you have to fix is the initial state, and to make it reasonable, we started from infinite temperature. So the idea is that if something is subdiffusive, even if you give it the most energy you can, then it could be even more subdiffusive if you go near the ground state, or in the classical case, near the borders of the energy distribution.
Okay, because my final remark is that if you go to dissipative spin systems like those for ferromagnets, when you do the quench in a dissipative system, this exponent that you call alpha, this is usually called lambda in that case, it is known that it is different from, from the correlation function, it gives different information with respect to the way for instance, interfaces move in the system. So interfaces can move by simple diffusion, but this exponent can be different due to the property of the autocorrelation function. I don't know if this is...
I'm not aware of this work. So here we're focusing on closed systems because we come from the community of like investigation of chaos in closed systems. But I think this should be interesting to be looked at. Actually, there are some people in the audience I saw that they are working at the interface between chaos in the closed system and what happens in terms of transport when you open a little bit the system as well.
Okay, thank you very much. If there are no other questions, I think we can move to the next speaker. There is one question, maybe, no? No, I don't see any. Stefano?
Stefan, sorry, I was muted. So is still around, Federico, or went away?
Yeah, I'm here.
Okay, so I'm curious about the algorithm. So you say you use symplectic, but the Hamiltonian is not separable. So do you have a trick for this symplectic algorithm?
No, of course it's so now I don't remember because we were discussing to use several. I don't remember which one was the one that we chose at the end. I think it's sort of Yoshida type in which you alternate.
Yeah, but exactly. So, but you don't have kinetic energy, no, because is a torque dynamics, no.
Mm-hmm.
So the Yoshida works for when the Hamiltonian is separable in P and Q. So I was wondering if you have a trick.
No, I actually don't remember now, but I can tell you in a second.
Okay, no, don't worry. You
okay.
Just send me an email.
So maybe later.
I will.
Yeah. Okay.
Thank you.
Okay, thank you, because we have to move to the next speaker.